Assalamu alaikum everybody. This is Saad Ahmed, and today we will be discussing about deep learning. Specifically, we'll be talking about the working and implementation of convolution neural networks, the CNNs. So let's start. Find this whole process. Okay, the convolution neural networks are basically the feed-forward networks. It's artificial neurons can respond to part of surrounding units within the coverage region. They perform excellently on the image processing and consists of convolution layer, pooling layer, and the fully connected layer. I'm going to show you how it works, but first look at this diagram at the bottom of your screen. You can see here that this is the input layer, this is the output layer, and we have 1 2 3 4 convolution layer, and 1 2 and 3 maximum pooling layers, and finally we have a fully connected layer, the network and the softnet function before the output is provided. So this is the basic architecture of this CNNs. Let's go into details of the working method of these CNNs and how they are able to classify the images. We will be starting with a very simple image, simple object, and then we'll try to understand the mathematics behind it. Okay, let's move on now. Let's try to understand the concept of the neural network by using this example where we would like to identify whether the input picture is X or an O. This is what we are going to classify, and we have a two-dimensional array of pixels, and 1 2 3 4 5 6 7 8 9 by 9 pixel, which contains the image. Then we have the CNN, which is going to classify. First it is going to learn and then classify the picture into an X, as an X or O. So this is basically what it is going to do. Okay, so for example, we have these two pictures, one representing X and the other representing O, and our target is to classify them either as X or O. Okay, the task on our hand is not that simple. We can have cases where there are different type of X that can be. So the task is not very simple. You can see that X can be written in many different ways, and O can also be small, large, or it can be thicker or thinner. So there are many things which are to be considered here, and this is what CNN needs to learn before it can actually identify an X or an O. Okay, deciding whether this X or A can be very easy for humans, but for computers it is going to be very difficult, because what computers sees is only the numbers, either 1 or -1. 1 is representing a bright box, and the -1 is representing a black box. So you can see here that it becomes very difficult. So the computer will not be able to identify it as a because only the matches are shown here with an X, and you can see this is not, only this part of it is identified by the. So if a computer tries to match it, only the central part will be able to only identify the central part, and the remaining, this part will be matched, as you can see in both pictures, but the remaining these ones are not in a same position, so the picture it will not be able to identify it here. So you can see that it will not be able to identify the image and will say that it's not the same picture, will not be able to classify. Now if we look at the convolution neural networks, what happens here is that convolution neural networks will be able to do it. What they do is basically they divide pictures into pieces like you can see here, and these pieces are compared with the pieces, and then neural networks, and these are called features. The features are basically parts of the image, and we are going to use these features to match and identify its position in the given image. So what happens next is that these are the pieces of the original picture, you can see, and they are identified, but the maths behind this is very simple. What it does is it's going to just multiply each pixel, each box, and then it adds up, divide by the total number of pixels in the features to get the final. So first box, you can see here that is multiplied by 1 multiplied by 1, so you get 1 and you put 1 here. Then you can move to the second box where minus 1 multiplied by minus 1 again gives you 1, and you have this answer. So it all adds up to 1 1 1 1, and when you get so, you have a perfect match. This is how it is done, and it keeps on doing. And finally what we do is add up all the values and divide by the total number of boxes, and you get the result 1, which is placed in the position, which identifies that this is the particular section of the image which is basically same. Then we move to the other and try to match it with the first feature. In this case you will not be able to get a perfect match because it's not the same thing. So you can see you will have some minus ones here, which shows that it is not the match. So this is the way. Again you will add up and divide by 9, you get a lesser value, and you put that value here, which shows that it is not matching the first feature, and 1 is showing that it is a perfect match. So you have different weights for different positions, and what it is happening here is that it continuously do this for every set of pixels, and this process is called filtering, and it is trying to identify every possible match. And after that we have a matrix, you can see here, with these horizontal diagonally we have higher values of 1 and 0.77, and elsewhere you can see the values are smaller. So this shows that it is a diagonal position. Next you can see that you are going to, this is the symbol for convolution, and, we just convolute for every feature. This was the feature 1, then feature 2, then feature 3, and we have all the values available, which shows again here you can see this is the match, and these values, and again this values, you can see that the values are larger which has a match and smaller which does not have a match. One image becomes a stack of filtered image, and this is what is done during the convolution layer. So this image have 3 features, and we have 3 piles. So now that again we will try to shrink the image by picking a window size of usually 2 or 3 and a stride of 2. Walk your window across your filtered image. From each window take the maximum value. This is what we are going to do in the next step, and this is called pooling layer. Pooling, and here you can see that in this particular section of the window 2 by 2 we have the maximum value of 1, so we put here 1, and similarly we will take the stride of 2, so it will move to this box. You can see again the maximum value is 3.33, and it continues like that. Here we will take this value, and it continues on and on until it fills the whole. So you can see here that here again we have ones, and the remaining are lower values. So this is again the maximum pooling, or the pooling layer, maximum pooling layer. Then comes the normalization, and in normalization what we do is we keep the math from breaking by tweaking each of the value just a bit. Change every negative to the 0. This is what we are going to do in normalization. This is the normalization, and you can see here this is the ReLU function, which we have already discussed in the previous session. So it is applied, and what it does, it is give you, whenever we have a negative value, it will convert it to 0. So we have zeros here, and all the zeros are marked which were negative before. So we have rectified the linear units. Next, a stack of images becomes a stack of images with no negative values. So we have on the left side stack of values with negative values, and now we have no negative values. These are the two things. Then okay, so we can see here that after applying the convolution layer, the ReLU function, and the pooling layer, we have a filtered portion of the image. What we can do here is that we can repeat these processes and find to filter it more, and you can see that the output of one becomes the input of the next. So this is how it is done, and when you see that you can repeat the layers, these two layers are repeated, then pooling function is performed, then this repeated, and the pooling function, and you see the images are becoming filtered and filtered, and you have a better results, which can be then become the input of the last layer, that is the output layer. So in the output layer you can so we have here the final section, that is the fully connected layer, in which what is happening here is that we have this set of filtered output which we are going to arrange in this way, starting from the top, and every box has a value in it. This will be applied to get the decision, the classification or category of the input picture, whether it is X or O. So what happens here now is, then we have each of the values are connected to or answers the classes, that is X and O. So you can see here that all are connected with, all the cells are connected with X, or you can call it votes. Okay, so these, each of these values are connected to the classes, that as these X and O, and similarly if and you can see here that the values, this box, this and these have higher values, so yeah, these they have a higher vote. And if you input an image of an O, you can see that the values here are different boxes have higher value, which shows that the values are, these values are high for O, so these votes have more values. So if you input a image of X, then we will consider those boxes, the ones which were identified before, and take their values, and you can see that the average comes out to be 0.92. And if we put an X into this, you can see that these are the values which have higher votes, so we just add them up and we have 0.51. So the classification made by CNN in this case will be X. So this is the basic process. You can just see that this is a fully connected layer, and this process can be repeated and to become a list of votes, and they can be stacked like this. You can have multiple fully connected layers to refine your classification process. So that was the basics of the convolution layer. There are other things also which has to be considered, but for now that is enough. We will now move on to the convolution calculation descriptions, and as shown before, you can have an image of 5 by 5, then we can filter it by 3 by 3, and the feature map can be also be of 3 by 3. And if you look at the calculation how it is done, so you can see here this was the feature map, and all the values are multiplied and the final answer is added up. So we have this value, and this is repeated to create the convoluted features. Some important convolution concepts. A convolution kernel is a matrix that is used to perform image scanning and convolution calculation based on certain rules. A convolution kernel can be used to extract local features, that is the target basically. The size can be different depending upon your requirement, the size of the kernel, the feature map, matrix generated by performing convolution using a kernel. Each kernel generates a feature map. If there are multiple convolution layers, a multi-layer feature map is generated, as we have seen in the previous example. Then feature map size, that depends on the requirement again. The size of the feature map can be described only by the width and the height. Stride is the number of pixels a kernel can be moved at a time an input image. If a kernel is moved one pixel at a time, it's called one stride, and I've shown you in the example that we have used stride as 2. And this is the zero padding to extract image edge information, ensure that the size of the output feature map meets the requirement. We can pad the input image with the zeros around the border. The value of padding equals to the border width in the pixel. Okay, look at this, the fully connected neural network and the locally connected neural network. For example, this is the fully connected neural network, which is with an image of 1000 by 1000, 1 million hidden units. That becomes this many 10 raised to the power 12 parameters, and the resources are wasted in this form. But if you use a locally connected neural network, you can see different points here focusing on different, and we have some 1 million hidden units only and 100 million parameters. So this is the advantage of locally connected neural networks, which are very useful. Okay, what we are going to do now, I'm going to show how the neural networks are practically implemented using Python, and I'm going to do a very basic task of identifying the handwritten digits, and I will be using a data set which is called MINST images, the MINST data set, MINIST, and it has around 60,000 handwritten digits, and which are labeled, that is annotated. And you can see on your screen that all the numbers written differently, like 3 here and 3 here, you can see they all are in different handwritings and labeled accordingly for the training purpose. Okay, so this is my Python interface, and I'm using Spider IDE for this demonstration, and I have my program here using the TensorFlow. You can see that I'm using TensorFlow, and if you have little idea about Python programming, that you know what I'm doing. Anyway, what I need to do or need to tell you here is that the main task is to understand how the neural networks are implemented, and we have seen that the data set, I told you about the data set, the image size is 28 by 28 pixels, and we need to flatten the image and make it 1 by 768 to be used for our classification purpose. And this is what I have done here. Then I have used this 128 neurons, and the activation function used is a ReLU function, and the output layer we have a softmax function for classifying the digits, which are 10 and from 0 to 9. So let's see how it is implemented. As you can see here that I have imported TensorFlow, the Matplotlib, and the NumPy. Then I have also imported the MINST dataset that I have told you about, and now I am going to proceed further by importing an image and then displaying it. So the image is displayed, and I'm going to you can see the image here, and it's 5. Now going back, this is the normalization process which we have discussed earlier, and we are normalizing the training data set, and now the testing data set. And you already know that the training and testing data sets are to be separate to get the proper results. Then we are going to build the model, and now we are going to add some layers, and now the hidden layers that I told you that for this we are using 128, and with the activation function of ReLU function, a softmax function at the output layer, and Atom optimizer. You can read it in the book if you want further details about it. And now we are going to start this training process, and we can see that the training process you can see that the training on 60,000 samples have started. This is the training process, which is going to take a little while. We'll just go through this process. We have 5 epochs for it, and finally we have this. Now let's see what is the next step. We will now evaluate the performance of our test data, and it is showing that it has achieved 95% accuracy, and you can see it here. Its test accuracy is 95%. And now for predictions, we are going to take a number image as a input, and we'll try to use this model to print out the number. So I'm taking this 2010 image number 2010 as an input image, and now let's see what it says. And it has printed the result as 1. Let's see, we'll see how it. So I'm going to check the image to confirm the result, and you can see that the image shown here is also 1. You can see it here. See, it's 1. Let's try another number here, and I'm going to predict image number. You can put any number here. It's, let's suppose it's 1000, and I'm going to also replace this with 1000 because I want to check the actual picture, actual input image. Now let's do it again. Let's see, it is predicting it as 9, and when I want to check this, I want to see it's you can see here it's 9. So basically, as we have seen, that it is very good in predicting the handwritten. You can try and make a data set of your own handwritings, and then try this model to predict the results. So this was it for today, and if you have any questions, you can definitely contact me for any issues or any concerns you have. Okay, then Take care. Allah Hafiz.